Right. Thank you, Yasuo, for the introduction, and thank you to the organizers for inviting me to give this talk. So I want to talk about the work that we and collaborators are doing towards engineering microbial consortia for critical mineral recovery with an emphasis on genomics-enabled approaches, which is my favorite. And this title has two meanings. Engineering from the GGI perspective, we're really thinking about engineering genes and protein function. And then I also work at the Molecular Foundry, which is a nanoscale science research center. And so engineering from that point of view is really thinking about how do we engineer materials. And so engineering living materials made from bacteria. So critical minerals and materials, what are these? So you've probably heard this term. This is, I love this figure from our colleagues at NETL. And this is showing the periodic table, which I hope you have stared at since you were in college. This graph shows the critical minerals list, which is maintained by the Department of Interior, and the critical materials list, which is maintained by the Department of Energy. And it covers a large chunk of the periodic table of elements. To orient you a little bit, these, for instance, are transition metals up here. This here is the lanthanide series, which covers the rare earth elements, which is probably what you're most familiar with when you've heard the term critical minerals and materials. Now, not all of these elements are created equal. So some of these elements, the market value is much higher. So some of the rare earth elements have a much larger market value than, for instance, some of the transition metals. And then also the Department of Energy, which is maintaining the critical materials list. Back in 2023, they came out with this assessment, which is showing which of those materials are more critical and more urgent than others. And you'll see the short term here is a little out of date. Since the short term is now in the past and the medium term is already here, the Department of Energy is coming out with a new assessment expected sometime this year. All right. How does an element make its way onto one of these lists? Well, so these are resources. These are minerals and materials which are vital to the US economy, and they're vital to our national security. And these elements have vulnerable supply chains. In some cases, there's no domestic supply of these minerals. And so this is, a strategic vulnerability. There are also elements that are needed in everyday life. So everyone in this room can reach out their hand and touch a critical mineral or material. Your phone, your laptop has these elements that are needed. Also, let's not forget that a lot of these minerals, the mining and refining practices can be very resource intensive. They can generate a lot of hazardous waste, and that can have negative impacts on both our environment as well as health. And so if we look at this list, some of you may recognize right away that a lot of these elements are actually known to be either essential nutrients for biological systems, or even if we don't understand the mechanisms, they're known to be beneficial for health. And then if we do a very cursory review of the literature, and this is not an exhaustive list, even more of these elements are known to be absorbed or taken up by organisms. And so this provides an exciting opportunity to leverage a lot of those processes, those mechanisms that biology has evolved to leach these materials from the environment, to uptake, to separate, to recover, to hyperaccumulate these metals. And we can leverage that understanding to develop technologies for a more sustainable bio-based recovery innovations. And so here, and it got a little pixelated. I apologize for that. So we're really interested in how can we contribute to decision cycles that given a particular target element, given a target source, which the source of these elements can be unconventional sources, think the mine tailing ponds, or perhaps soils. How can we generate genome-based information to feed into decisions we make with respect to selecting strains for these technologies or even engineering strains? And then how does that fit into more of a scale-up and techno-economic analysis of is incorporating biology into a technology going to be profitable and sustainable? And so everyone in this room, whether you know it or not, if you're working on a biological system, which I think we all are, then you have worked with critical minerals and materials. And so I hope everyone is able to see how their research can impact our goal to develop new technologies for mining and recovering these materials. And so, for instance, I've just provided some cartoons of different strategies that are possible with respect, for instance, for my colleagues out there that work on plants, of developing agricultural systems for the mining, the phytomining of these elements from soil. For those of you who work on biogeochemical cycling and microbial communities in the soil, in the rhizosphere, these microbes are extremely important in the cycles that are involved in actually affecting the bioavailability of these metals to plants. We also have cases of where you can imagine microbial systems being used to recover these metals from wastewater, from e-waste, you name it. There's going to be lots of different solutions for this problem. And then in the last 2 minutes, I'm going to give a shameless plug for, I think, to develop these biorecovery strategies, whether you're thinking about developing phytomining applications or you're thinking about developing microbes for the hyperaccumulation and the recovery of these metals, we really need to bring together both the systems and systems engineering together with thinking about the interactions between biology and metals, which is actually happening at the nanoscale. And so we have this pilot user proposal call that's open now. Please find me if you're interested in applying to this call, where you can apply for resources at the JGI, as well as work with our scientists at the Molecular Foundry. And we really want to empower you, the users, to accelerate the recovery, reuse, replacement, transformation of these metals. We really want to advance biodesign and systems biology approaches grounded in this nanoscale understanding, and ultimately develop new biotechnologies for novel mining, extraction, and utilization. And if you are interested in applying to this user call, we have lots of useful links for you to follow. And with that, thank you.